All right, hello everybody. So here we're going to talk about Quicksort, which is the other like big n log n time sorting algorithm based on an operation called a partition. Merge sort was based on an operation called merge, so of course Quicksort is based on an operation called partition. So theoretically, Quicksort has a worst case of O of n squared, but it's pretty easy to avoid that in practice. All right, so what's a partition? How's a partition work here? So the idea of a partition is we have an unsorted sequence, right? So unlike merge sort, we don't require the input sequence to have any kind of like structure to it for like a merge there or something like that. So we just have an unsorted sequence here. The partition is going to move small values to the left half and large values to the right half there. We define small and large relative to a pivot value that we'll call P, and that's just going to be some value that we'll pull from the sequence. We'll talk later about like how do you pick the pivot value, but for right now, just assume that we've pulled some value from the sequence. That's our pivot. Values that are less than or equal to that are going to show up on the left, and values that are greater than or equal to that are going to end up on the right half there. The pivot itself might be on the left or the right half there, sort of depending on like how the algorithm sort of works there like that. So that's why it's less than or equal to and greater than or equal to. Partition is done in place, so unlike a merge, we're not like moving stuff from one array to another, and it runs in linear time there. All right, so how do we like accomplish this, right? So here's an example. So let's say that we have this sequence here, and we pick 5 to be our pivot here like that. So when we're done partitioning, we want all the values that are less than or equal to 5 to be on the left, and all the values that are greater than or equal to 5 to end up on the right. In this case, 5 ended up on the right, but it wouldn't necessarily end up there, right? It might just as well have ended up on the left there like that. The other thing to notice is like we're not doing a full sort, right? Like the left half here is not sorted. The right half is sorted, but that's purely by chance, right? Like it might not have ended up sorted there like that. All we're trying to do is put small things on the left and big things on the right there like that. Just some notes that like might not be immediately obvious. So depending on what we pick for our pivot, the partitions may end up being more or less like sort of balanced in terms of their size. So like for merge, we always split it exactly down the middle. For partition, we can end up with like 1/3, 2/3, or 1/4, 3/4, depending on what value we pick for the pivot value there like that. So a good pivot is of course one that sort of like equally balances the two halves there like that. And again, we'll talk about how do you pick a good pivot later on there like that. Like we said, the pivot value itself might end up on the left or the right half there. There's some versions of partitions that always sort of like make sure that the pivot ends up exactly in the middle. So you actually have like sort of 3 sections, less than, equal to, and greater than. But that's more work, so we're not going to do that. And then finally, if there's multiple copies of the pivot value, then some of them might end up on the left, and some of them might end up on the right there like that. So if you had like 7 5s in there or something like that, they might end up distributed between the two halves. Okay. So we want to implement this such that it runs in linear time and operates in place using only a constant amount of memory. So let's just say that we're like we're looping through our sequence from left to right as one does, right? And we find an element that belongs on the right. So again, we're sort of picking our pivot to be 5 here. So since 9 is greater than or equal to 5, that means 9 belongs on the other side there. So one thing we could do, right, is we could erase 9, which would shift everything after it down, and then sort of like insert 9 at the end there like that. Sort of move 9 from the beginning to the end of it there like that. But that erase would require a nested loop to shift everything down, and then that would turn this into a O of n squared runtime. So we don't want to do that. We don't want to do something that requires like shifting the other elements around there like that. So the idea is 9 by itself is not enough. Instead, what we want is something over here on the left, like 9, that is greater than our pivot, and then we also want to find something on the right that is less than our pivot. We're looking for partners here because then 9 needs to go over here and -2 needs to go over there, so we can swap them. And a swap is a constant time operation, right? It's not like shifting anything other than those two elements here. So we take the sequence up here, we swap the -2, and the 9. And now I have, something that is less than or equal to 5 on the left and something that is greater than or equal to 5 on the right. And then we just sort of keep working towards the middle there like that until we, meet in the middle, hopefully. So we're going to have two indexes here. We're going to have I that starts on the left and j that starts on the right. I is looking for a value that is greater than or equal to the pivot. So we're looking from over here, and we're looking for something that is too big, something that is greater than or equal to our pivot. And then j starts over here and is looking for the opposite. It's looking for something that is too small, that is less than or equal to the pivot there like that. If I ever crosses over j, then that means all the values are in their right spots, right? That means all the values on the left are less than or equal to, all the values on the right are greater than or equal to. And then wherever that happens, j plus 1 is the location of the split point, of like the sort of dividing line between the left and right partitions there. So the algorithm is like this. We pick our pivot value to be something. Again, we'll talk about how do we pick a pivot later. We're going to initialize I to -1 and j to size. Now, one thing to notice is both of these are sort of like one step outside of the sequence. And that's because the first thing we're going to do inside of our loop is actually increment I and decrement j. So we start them one outside because we're going to move them inside the very first thing we do here. So then we do a nested loop where we increment I until we find something that belongs on the right. All right, so I is looking for something that goes on the right-hand side. And then we do another nested loop where we decrement j until we find something that belongs on the left. Right? I is starting on the left, looking for things that would go on the right. J is starting on the right, looking for things that go on the left. If they cross over, that means we're done. So j plus 1 is the split point there. Otherwise, we swap them, and then we cycle back around here, and we look for another pair. Now, you might be sort of like, yelling at your video player in your browser here. Well, wait, I thought you said we wanted to avoid nested loop, and steps 3 and 4 are both nested loops. That's true, but we never reset I and j back to the beginning, right? Like I never, inside of the loop, I'm not like, okay, go back to the beginning and search again here. So I and j are always progressing towards the center of the sequence. So it's not really a true nested loop in here, and in fact, I'll show you a version of this that does not have a nested loop at all, but that's equivalent to the sort of, the natural way to write this out here. So here's the sort of algorithm as written out, right? So I starts at -1, j starts at size. So this here is like, all right, we're looking for something that's too big. There. And then this one here is trying to find something that is too small. Right. So we're looking for something on the left that is too big and should go on the right, and looking for something on the right that's too small that should go on the left there like that. These are while loops, right? So we're saying as long as the sequence elements are less than the pivot, so that means this is going to stop at the first value that is greater than or equal to the pivot. Likewise here, this is greater than, so that means this is going to stop at the first value that is less than or equal to the pivot. If they cross over, we're done, so we return j plus 1. Otherwise, we do the swap, and then we look for another pair there like that. So let's run it on this sequence here. This is not the same sequence as before, as a different one here, but we'll run it on this sequence with a pivot value of 7 to sort of see how it works. So we start I at -1 and j at n. We run the first loop for I, so I is scanning forward, looking for something that is greater than or equal to p, right? Our loop is while the elements are less than p, so 3 is less than 7, 2 is less than 7, 10, or 10 is greater than or equal to 7. So that is where I stops. I stops at index 2. Then the j loop runs. So again, j is looking for things that are less than or equal to the pivot. So 8 is greater than the pivot. It belongs on the right. It's fine. It can stay there, right? -2 is less than or equal to 7. It belongs on the other side. So 10 needs to go over there. -2 needs to go over there. So we found a pair. So we're going to swap, right? -2 is on the left and 10 is on the right. So now notice that like these things here are all less than or equal to 7, right? And these things here are all greater than or equal to 7. So I'm sort of building up the left and right partitions bit by bit here. Then I continues searching, right? So I doesn't start over from the beginning and go like that. It starts from where it left off in the last search, which is why this isn't a true nested loop here. So again, we're looking for something that is greater than or equal to 7. 5 is less than 7, so it's fine. 12 is the first value we discover that is greater than or equal to 7, so we're going to stop there. Then we do the same thing with j, right? And it just literally stops at the next thing. This is less than or equal to 7, and it stops there. Now, of course, that is 7 itself. You might wonder, like, why, like, we're going to swap 12 and 7 now, right? We're going to say, oh, 12 goes over there and 7 goes over there. But the 7 doesn't have to move, right? The 7 could stay on sort of either side there. So, like, why do we consider the pivot value as, like, a candidate to be moved to the other side? Like, wouldn't it be better to, like, you know, sort of leave the pivot where it is? Well, it turns out that, like, if we consider the pivot to be a candidate for moving, it gives us more options, right? Like, it's sort of like, now I have something that I can move this sort of 12 with here like that. Whereas if I didn't consider 7, maybe I'd have to sort of search further there. So it's actually better to move the pivot than to not move the pivot. It gives us more, like, options for finding partners there. So we swap those two there like that, right? And then we continue our search. So I is going to stop at the 12 that we just moved, right? This is the first value that we find that is greater than or equal to 7 going that direction. And then j is going to stop at the 7 that we just moved. That's the first value that is less than or equal to 7 there. So they cross over each other. And then at that point, the dividing line is j plus 1. So the left partition starts here. This is all the stuff that is greater than or equal to 7. And then everything up to that point is less than or equal to 7. So our final partitions are 5 elements on the left and 3 elements on the right. If we'd picked a different pivot, of course, then we would have ended up with different sized partitions. Like different things would have ended up on the left and on the right-hand side there like that. So like I was saying, the nested loops doesn't make it like completely obvious that this is an O of n time algorithm here. So this is a version where I've flattened the nested loops into the main loop. So I got rid of the sort of do while loops that used to be there, and I just have a straight increment for I and a straight decrement for j. So every time this loop runs, we increment I once, I moves that way, right? And we decrement j once, j moves that way. So again, if they cross over each other, that means we're done and we return j plus 1. But if they haven't crossed over each other, we check to see, have we found a partner pair? Have we found something on the left that belongs on the right and something on the right that belongs on the left? And if they have, we swap them there like that. So since I starts at -1 and j starts at size, and we always increment I and decrement j, this is going to run n over 2 plus 1 iterations. Everything we're doing in here is O of 1, right? So if you throw that inside of a big O, right, n over 2 plus 1, that simplifies down to just big O of n. So this version should be equivalent, unless I screwed something up, should be equivalent to the previous version, but makes it a little bit more clear that this is in fact a linear time algorithm. So just some details about partition. So we usually require that the pivot value be chosen from the elements in the sequence. If you want to get technical, the pivot doesn't have to be one of the values in the sequence. It could be like the average of the values in the sequence or something like that. What you definitely do not want to do is pick a pivot value that is smaller than everything in the sequence or larger than everything in the sequence. If you do that, right, then like the nested do while loops will just keep going all the way past the end of the array there, and then you'll be out, sort of out of bounds, and bad things will happen to you there. So whatever value you pick for the pivot, it should be a value sort of in the range of the values in the sequence, but it doesn't strictly have to be one of the values from the sequence. But usually it's the easiest thing is just like, grab one of the values from the sequence there. The return value from partition is the split point. It tells you the index of the beginning of the right half. So my left half and my right half, partition returns the index of the beginning of the right half. Or equivalently, it's the size of the left half, the number of things that are in the left partition there, like that. We always increment I at least once, right? And we always decrement J at least once. We have do while loops doing that, so they always run their bodies at least once. So it's not possible that partition would return n plus 1, like that, right? But it might return n, like this. So there's specific circumstances, if the sequence is already sorted, partition may give you an empty right partitions. And that's something we want to avoid here. So we'll take a look at that here like that. So let's say that our sequence looks like this, right? It's already sorted and we pick the largest value as our pivot value. So I is going to work from left to right, looking for something that is greater than or equal to 5. So I is going to stop there. 5 is the first thing we find that is greater than or equal to 5 there, like that. Now, real quick here, like notice what would happen if I had picked a pivot value of, say, like 100, like a pivot value that is outside of the range of the values in the sequence here. Then I would have just walked off the end of the array looking for something greater than or equal to 100. I'd be out of bounds on my array, and terrible things would happen to me, and demons would fly out of my computer or whatever. So we definitely want to pick our pivot value that is in the range of the sequence, and 5 is in the range of the sequence, so it should be okay, right? And then J is going to do the opposite, right? J is looking for something that is less than or equal to 5, so I and J stop in the same place. And then what are we going to return? We're going to return J plus 1. So the dividing line between the two partitions is here. This is the left partition, and then the right partition is empty. Our final partitions are everything on the left and nothing on the right. The empty partition isn't really a problem. What is a problem is having everything that we started with be in the sort of starting partition there, like that, right? Like ending up with a partition that is exactly the same as what we started with, because we're going to be doing recursion on these partitions, so we need them to be smaller than what we started with in order for the recursion to be valid. So what we can do is we can just fix this manually. After we get the split point from the partition function, we check to see if it looks like this, if it is like everything on the left and nothing on the right, and then we just manually convert it to, okay, one thing on the right and then everything else on the left here. I'm just moving the split point. So like if the split point is here, let me get a different color, right? The split point is here like that, right? I'm just, by decrementing mid, I'm just moving the split point over to be like that, so that it's 1, 2, 3, 4, and then 5 on the other side there like that. So that ensures that like both of my partitions are non-empty, and neither of them has the same size as what we started with. Okay, so how do we turn this into a sorting algorithm, right? We don't just want to like write a partition thing here, we want to sort. So the answer is actually pretty easy. Just partition the partitions. So again, we're starting from the same sequence with a pivot value of 7, and that gave us these partitions right here. So then I'm just going to pick a pivot value for the left and a pivot value for the right, and then repartition them. So if I repartition the left half and the right half, I get these partitions. Left, right, like that. My base case is when I have a partition of size 1, because size 1 doesn't need to be sorted. So the 8 is sort of done there like that. And then I'm just going to repartition all of these ones that are greater than 1. So those split up again like that. I only have one partition left that needs to be split like that. So that splits it up like that. Now remember that partition is in place, right? So even though I've drawn these things sort of being spaced out like this, in reality, they are all still in the same array here. So I've just been rearranging stuff within the array. I end up with -2, 2, 3, 5, 7, 8, 10, and 12 here, right? We are done. The sequence is sorted like that. So the actual implementation of Quicksort is pretty easy. If your size is 0 or 1, we're done. Otherwise, we partition the sequence, and then we recursively sort the left partition, and we recursively sort the right partition. We sort of arranged so that like partition never returns an empty partition, so the n equals 0 case here doesn't happen during the recursion, but you might call the recursion, the quicksort function on an empty sequence, so we want to make sure that we can handle that. There's nothing invalid about trying to sort an empty sequence, right? So here's the quicksort algorithm, right? We have two base cases, size equals 0, size equals 1. You could, of course, combine those with like an OR if you wanted to. Otherwise, we partition. That tells us the split point. We fix empty partitions if we have them. And then we just recursively sort the left partition and recursively sort the right partition here. So the left partition, right, has size mid. So it goes from 0 to mid minus 1. And then the right partition starts at mid and goes to size minus 1. So the size of the right partition is size minus mid. We're doing pointer arithmetic here. If you need a review on pointer arithmetic, there's a video way back at the beginning about that there. But when we do seek, right, plus mid, that is equivalent to saying I want the address of the mid element in the seek array, or like that. That's basically what we're doing is we're saying, hey, give me a pointer to the beginning of the right partition there like that, and then we just recursively resort that. All right, so now let's analyze quicksort here. So the analysis of quicksort depends on the midpoints that partition gives us here. So if partition consistently sort of splits things equally in half, then our runtime is going to be n log n. Partition runs in O of n time. It'll take us log of n sort of levels to get down to the size 0 or 1 there like that. So n times log of n gives me n log n there like that. But there's no guarantee, unlike merge sort, that partition will always split exactly in half here. It can give me like really unbalanced partitions, like n minus 1 or 1, and then my runtime would degrade to O of n squared. If partition is just giving me one thing on the left and n minus 1 things on the right, it's going to take me n levels down to sort of get all the way down to the base case, and then each sort of horizontal stripe is going to take me n time. So I have n times n, which is going to give me O of n squared there. So the key to ensuring that we get an n log n runtime is picking good pivot values. All right, so there's like some bad choices for the pivot and some good choices for the pivot here. So our bad choices for the pivot would be to pick either the first or last values in the sequence there. And those are bad choices because if our sequence is already sorted, right, then where's the smallest value going to be? It's going to be the first value. And where's the largest value going to be? It's going to be the last value. So if we pick the smallest or the largest values as our pivot, then we end up with these like sort of maximally unbalanced partitions, like n minus 1 and 1, and that gives us our worst case runtime. This is like the opposite of an adaptive sort, right? Where it's like, oh, my sequence is already sorted, well, you get O of n squared. So a good choice for the pivot, like the best possible choice would be to pick the median value. But what do you need to get the median? You need the sequence to be sorted, and sorting is what we're trying to do. So, like, you know, it's possible. We'll look at the quick select algorithm in a little bit here, but like normally we don't sort of like go to the work of actually finding the median value for the pivot, because if you just pick a pivot at random, yeah, you might pick a bad pivot like once in a while, but you're unlikely to pick the bad pivot like over and over and over all the way down there. So as long as we're not picking terrible pivots like the whole way down through the recursion, it's sort of okay. If you want to sort of get a little bit of extra insurance, you can pick 3 values at random from your sequence and then take the median of those 3. If you just have 3 values, finding the median is easy. Like you just get the smallest value, the largest value, and then the median is the other one. So like, computationally, that's not too bad. You do have to be a little bit careful about how you pick your 3 values, because you can't just pick 3 indexes at random, because you might pick the same index twice, or the same index like all 3 times, and then you're not really getting the median of 3. So you have to pick like an index at random, and then pick another index, but make sure it's not the same as the first one, and so forth there. But it's not like, it's not that hard, right? So if you want that extra insurance, you can do something like that. So with that in place, we have quicksort as an n log of n time sort of in place sorting algorithm here. As long as you sort of like do a good job of picking your pivot, it tends to be faster in practice than merge sort. But unlike merge sort, you can't use it on a linked list, right? In assignment 3, you did merge sort on linked lists here. You can't do that with quicksort. Quicksort is more of a sort of like random access kind of thing there. If you want to get technical about it here, like Quicksort does use log of n stack space for its recursion, so it's like it's using more than a constant amount of memory, but we usually will sort of like fudge that and say it's still in place because we're not copying the sequence there like that. So yeah, that's Quicksort. If you want, you can hop over into the quick select video for an algorithm for finding the median that is really similar to Quicksort there. But otherwise, that's it for now.